I'm a bit hoarse today. I was sick last week. My voice is still coming back, so I'm using the microphone very closely. I made sure that this time the microphone works. Okay. Welcome. Today we're going to have, I think, an easy lesson in preparation to the quiz. I want to make. Wait.
Should I move it right
Yeah,
now?
you can sit over there, but the camera.
Oh, okay.
Leave the camera as it is.
Okay.
This time I tried to put the camera in the center of the room instead of to the side, so maybe it'll be a bit of a better quality. Okay? Can you make sure that the cup of coffee doesn't sit in the frame?
It doesn't.
Okay.
We're good.
Okay. So one small thing I want to make sure is clear before we start with today's lesson. Something that I said about plan comparisons last week. Okay, I gave you a rule about k minus 1 orthogonal comparisons. Okay, I told you that a full orthogonal set of comparisons has a maximum of k minus 1 comparisons. Okay, but that's the maximum number. Okay, I can have less than k minus 1 comparisons. I don't have to conduct k minus 1 comparisons. So let's say I have 6 groups. Okay, I'll try to put it even closer. Okay, let's say I have 6 groups, okay? I don't have to conduct 5 comparisons. Okay? Shh, everyone. Even with the microphone, a bit low today, So again, if I have 6 groups, I don't have to conduct 5 planned comparisons. It is my prerogative to conduct 3 planned comparisons, right? But the maximum amount of planned comparisons I will conduct is k minus 1. Okay? So you don't have to conduct k minus 1, but that's the maximum you're allowed to conduct.
Always? I mean, like the maximum could be 6?
The maximum will be k minus 1. So if I have 6 groups, the maximum will be 5. Okay? Okay. Moving on to post-hoc tests. So ask them throughout the lesson. Okay, I don't want to miss any material that will be on the quiz. So if we'll have time before the quiz, feel free to ask. Okay, I wouldn't mind answering. And a lot of the questions that are in the quiz will be referred to within the lesson. Okay, so it's not a problem. Okay, here's the story today. Again, a topic that I'll enjoy. So, Jerry Seinfeld wants to know which of his friends is the funniest stand-up comedian. Okay, so I love stand-up comedy. So we have different stand-up comedians. He measured the amount of laughter the comedians received over 10 shows each. 10 shows each. Okay, so we have different comedians. Each one goes to 10 shows. Okay, and each one gets different amount of laughter in each one of the shows. So in a way, each show is one observation. Okay? Each show is one observation. The dependent measure was the volume of laughter in decibels. We wanted to conduct all the possible comparisons between all the comedians. We have no hypotheses in advance. So already we have a lot of information that tells us that we cannot conduct planned comparisons. Okay? We cannot conduct planned comparisons. Why? Because, first of all, he had too many comparisons. Okay? He wanted to compare between all the comedians. So, let's say we have, these are Seinfeld friends, and Seinfeld himself. So Chris Rock, Wanda Sykes, Sarah Silverman, Aziz Ansari, and Louis C.K. Okay? Yeah.
Sorry, real quick. How do you know when it's too many? Like,
Again, more than k minus 1.
but what's k minus 1? Yeah, I don't know what's k minus 1.
So here, what's k minus 1? 6 comedians. What's the maximum? 5. So if I want to conduct all the comparisons, right? So Seinfeld versus Chris Rock, one side, Sarah Silverman, that's already 5 comparisons. But he also wants to compare Chris Rock to the rest. And he also wants to compare Wanda Sykes to the rest. And Sarah Silverman, it's too many comparisons. Okay? He cannot conduct all these comparisons using planned comparisons. We went way over the k-1 rule. So we have 15 paired comparisons. That's just the paired comparison. I'll remind you the problem of family-wise alpha. Okay? Family-wise alpha is the chance of making at least one type 1 error. Okay, at least one. And we said that the more comparisons we conduct, the larger the chance to make type 1 error. How much larger? By using this formula. Okay. 1 minus 1 minus alpha in the power of the number of comparisons. So if we conduct 15 comparisons, we have 54% of making at least one type 1 error. Okay? That's a huge amount of making type 1 errors. So, of course, we have to control for alpha inflation, right? This is alpha inflation. From 5%, we got into 54% of making at least one. Okay, so of course we have to control the alpha, and we have 2 methods of controlling the alpha. We have to conduct a test to correct for alpha inflation. Okay, so here's a flow chart. Okay, how to decide, are we conducting a planned comparison or are we conducting a post-hoc test? So the first question is a multiple question, right? All of these answers have to be yes in order for us to have a planned comparison. So is it a planned theory-driven prediction? Right? Because the first step of planned comparison is that they have to be planned in advance. Right? They have to be planned in advance. We can't just go into a data set and look at the averages and say, oh, these two look different. Let's compare between them using a planned comparison. No, it doesn't work like that. It has to be planned in advance. But that's not the only rule. The set of comparisons must be orthogonal. Okay, and we spent throughout last lesson discussing what does it mean for a set of comparisons to be orthogonal. Okay, the entire set must be orthogonal. And if the set is not orthogonal, we can't conduct planned comparisons. So if the answer is yes to both questions, we can conduct planned comparisons. Just a sec. And I've written here in parentheses, ANOVA plus planned comparisons. Why? Because even though you don't have to conduct the ANOVA, you're still allowed to conduct both ANOVA and planned comparisons. Okay? So the researcher can go into the study, conduct the ANOVA, okay, look at the ANOVA, and then also conduct planned comparisons.
Is it recommended to do that?
Again?
Is it recommended to do that?
It's the norm to do that. Okay, I can't say it's recommended, but that's the norm. Yes.
When you say the whole set is orthogonal, that means that k minus 1 is going to that set.
So again, we have
Like
a few
if you
rules.
7 and 6.
A maximum of k minus 1. Okay? But all of the comparisons must be orthogonal to one another. Right? Knowing that I have 6 comparisons, six comparisons in a group of 7, right? Doesn't mean that the set is orthogonal. Okay? I can have a non-orthogonal
Oh,
set.
so you mean the data set has to be orthogonal?
The comparisons, right? What's an
They all
orthogonal
have to equal
comparison?
0?
All of them, yes.
Okay.
Right?
Yeah.
So the weights must be orthogonal. Yes, you want to ask.
What does omnibus mean? Is it just ANOVA?
It's just the overall ANOVA.
Okay, and the Levine's theory or whatever, what is that?
Levine's test, that's to compare the equivariant assumption. So that's separate to the.
No, is it?
Okay. So under all these conditions, we can conduct plan comparisons and deal. If one of the answers here is no, okay, then we can't conduct plan comparisons, right? Plan comparisons have very strict rules. If the answer is no, we must begin with ANOVA. Okay, we have to begin with the ANOVA. And then ask ourselves, is the ANOVA significant? I'm going to remind you, what does it mean to have a significant ANOVA? Just a sec, I'll finish this. If the ANOVA is significant, we can conduct post-hoc tests. Only if the ANOVA is significant, we can conduct post-hoc tests. Meaning that if the ANOVA is not significant, then we stop. Okay? If we didn't plan comparisons and the ANOVA is not significant, then we stop. That's it. There's no difference between the groups and we stop. Yes?
I have this question that when you say set of comparisons orthogonal,
Yeah.
if you have three comparisons, they all need to be orthogonal.
Yes,
If
exactly.
you have four, they
All have to be orthogonal. Exactly.
One of them is not
The entire set. You can say a rotten apple spoils the barrel, right? Yes.
The only time we'd use a post-hoc test is like if we have too many, because we can make it orthogonal.
Not necessarily, because yes, if you have too many,
That's the
but
only time
also if you're interested in a non-orthogonal set of comparisons, that's fine. You're allowed to be interested in a non-orthogonal set, right? The researcher can't shove their hypotheses into an orthogonal set. Then they won't conduct them comparisons. They'll simply conduct an ANOVA and post-hoc tests. That's completely fine. Yes. So we'll discuss that today. Okay, the first thing I want you to know at this point is that you don't conduct post-hoc tests if the ANOVA is not significant. Okay. It's you don't have to do the ANOVA. You can do the ANOVA, you don't have to do the ANOVA. Okay? Okay. It's interesting the vibe in the room. Okay? Because for me as a teacher, I hate to see you stressed. I hate to see you stressed. I love that everyone is relaxed. But if you're not stressed, a lot of people won't show up and people will be in their computers, and so we don't know what we prefer. But I'm sorry that you're stressed, but at least there's electric energy in the room. Okay, so that's the first step. Now, so we said that we can't conduct plan comparisons, right? We have too many comparisons, the set is not orthogonal. So we have to conduct post-hoc. But first of all, we have to conduct an ANOVA. Okay, we have to make sure that the ANOVA is significant. So here are the averages. Okay, so I remind you that's the average decibels, right? For each stand-up comedian, we have 10 observations. Okay, so 10 shows from Seinfeld, 10 shows from Chris Rock, 10 shows from On the Sides, so on and so on and so on. That's the average decibels of laughter for each comedian. Okay. So we have all of these, and we can calculate SSD. SSW is given, okay? Given by who? Given by me, okay? I'm giving you SSW. And the number of participant observations, right, is 60. Because we have 10 observations per comedian. So from this we can calculate MSB. MSB is the sum of squares between the groups divided by k minus 1. Notice this is the ANOVA, right? The overall ANOVA. How many groups do we have in the overall ANOVA? 6, right? So 6 minus 1. So we get that MSB is 680. Okay. What does that mean? Not a lot, because we have to compare MSB to MSW. So SSW is this. MSW is this, right? MSW is the sum of squares within divided by degrees of freedom within, and we get 4,400 divided by 55, we get 8. Again?
N minus k.
Yeah, n minus k. 60 people?
54.
Ah, right, 54. Okay, let's imagine there's 61 people. Okay, so it will be easier for me in this presentation. Okay, so Seinfeld has one more participant. Okay, it'll be easier for me. So MSW, I'm writing it down for future reference, and DFW is, let's keep it at 55. Okay. Imagine one more. MSB is this, MSW is this. We can calculate F, right? F, the ratio between the obtained difference versus the difference expected by chance. And we get 8.5. To know what does that mean, we have to compare it to the critical F. So this is the critical F for 5 degrees of freedom between and 55 within, so it's 2.4. Just a sec. I'm writing this down for future reference as well. Yes? So think about what we're asking. We're asking about the difference between the groups, right? So the F represents, this F represents the difference between the groups. How bigger is the difference between the groups as compared to chance, right? So we can't have a different F for each group. We only have one F for all the groups, okay? We always compare groups. That's the ANOVA. That's the ANOVA. So our calculated F is larger than the critical F, meaning that we have a significant result, right? A significant result, the likelihood to get this result by chance is less than 5%. Oh, it's such a low chance to get it by, it's just such a low probability to get it by chance, it's probably a real result. Okay. Now, what does that mean? First of all, yes. Let's remind ourselves about the meaning of a significant ANOVA. The result was significant. What can Seinfeld conclude? So the null hypothesis in ANOVA is that all the groups are equal to one another, right? There's no difference between the comedians, right? They're all equally funny. So we rejected the null hypothesis, right? We rejected the null hypothesis, but what does that mean? All it means is that there is some difference between the groups. At least one of the comedians is funnier or less funny than the rest. Or maybe two of them. Or maybe only two of them are different from one another. Okay? There is some kind of difference. But we don't know at this point what is the difference. Rejecting the null hypothesis in ANOVA, all it tells us is that not all the groups are equal. And that's it. And that's not a satisfying conclusion, right? We said before, if you have a drug company, you test 5 different drugs, and all this, what the scientists can tell you is, look, the different drugs are different, right? They have different effects. and you ask, okay, but which one is better? Oh, we can't tell you that. So. That's not enough, right? We don't know at this point which one is the best, so we have to continue. Yes?
Wait, so if it is significant, you reject it? Or
If it's significant, we reject the null hypothesis. Right? Because the null hypothesis will tell us that everything is random. Everything is equal to one another. There are no systematic differences. Rejecting the null hypothesis simply says, look, there is some kind of difference. Someone wants, yeah.
Nobody tells you that it's different, and then you can go back and look at the means, and that tells you what the exact difference is.
But look at the numbers, right? So can you tell me for sure that is Seinfeld better than Louis C.K.?
No, but I can tell you that Seinfeld is better than.
Right. You might have some of the information, right? But you can't tell me if all the differences are significant. And we want to know in this case who's best. So there is some kind of difference. ANOVA tells us that not all the groups are equal. At least one of the groups or more are different from the others. ANOVA does not tell us which group is different from the others. Okay, that's an important thing to know. That's a limitation of the method. Once we know that there is some kind of difference, the ANOVA, we want to ask, what is the source of this difference? Right? We found some kind of between groups difference. By asking what is the source of the difference, we can ask which group is different from the other. So if the source of the difference is that Seinfeld is better from everyone else, that's one answer. But maybe the source of the ANOVA, the significant ANOVA, is that Seinfeld is only better than Wanda Sykes. Okay? We have all these options. And we have to have post-hoc tests in order to answer this question. Okay. Any questions to this point? Yeah.
It's a little bit of a long process,
Mm-hmm.
in a sense that it doesn't seem very, not convenient, but is there not a better way to do this? I mean, it just seems like an arduous process.
Mm-hmm.
Why would we have a test that just tells us there is a difference, and we do another test that tells us which one of those? So a t-test tells us there's a difference, and it's this one. Why don't we have one test that does it all?
So, in terms of calculation, each time you're looking at different parts of the between group variance. You can't do both this and a part of it. Now, think about this sentence and think about why don't we do post-hoc tests if the ANOVA is not significant?
I was also thinking, why don't we just do the post-hoc test in general, we're not doing the ANOVA, because it tells us which one's different enough, so wouldn't that kind of answer the significance that they're different already?
Yes, but first of all, the post-hoc test asks what is the source of the between groups difference. Okay. So if there is a source, right? Sorry, I'll take it back. First of all, we ask, are there any differences? And then we ask, what is the source of the differences? If there are no between group differences, there is no reason to ask the second question.
Or could we just start with the second question?
Okay, you both have good intuition. I can tell you that there is a method that we're not studying in this course, which is simply skipping, okay, and do a very restricted post-hoc test to begin with, okay. But that's not part of the material, okay. But you do have good intuition. We consider the post-hoc tests. Why are they called post-hoc? Post-hoc is after the math, right? So only after we said that there are some differences are we allowed to ask, what are these differences, right? And if the ANOVA is not significant, what is the conclusion here? If the ANOVA is not significant, we say there are no differences, even though we can see in our eyes look, there are some differences between the averages. Not rejecting the null hypothesis, okay, will tell us that we cannot conclude about any differences. The only conclusion we can have is that we found no differences between the groups, in this case between the comedians. So if we found no differences between the groups, how can we ask, so what is the source of the differences? There are no differences. Yes?
So do you just stop there?
You stop there, right?
So you just don't
Just like a t-test, right? You do a t-test. If it's significant, it's significant. If it's not, it's not. If the ANOVA is not significant, you stop. Exactly. Okay, that's true for post-hoc. Again, I remind you that if my set of comparisons is orthogonal, I'm allowed to do planned comparisons even though the ANOVA is not significant. Okay?
Okay.
Only if I have planned comparisons am I allowed to conduct any further tests, even though the ANOVA is not significant. Okay, is the idea that post-hoc tests are meant to evaluate the source of the difference clear? Is it clear that we don't do post-hoc tests if the ANOVA is not significant, and why? Okay. Already, this means you already have probably one question in the quiz correct.
Wait, what? No,
I said the word quiz. It was my
Yeah.
Obviously, if we have a lesson about post-hoc tests, one of the questions will be about post-hoc tests, right? You have a few places in the front if you're willing.
No quiz?
Yes.
Quiz job.
Nova is
Okay, yes.
they do post hoc tests. If there's not significant, you just you don't do it in yourself.
How few is a few? Okay. So, as we said, the rule for conducting planned comparisons is that the set has to be planned and orthogonal. Orthogonal has several rules of its own. For it to be orthogonal, it has to be all the comparisons must be independent from one another. So that will keep the number of comparisons you're allowed to do as a few comparisons. You simply won't be allowed to conduct any more comparisons. It depends. That's the K-1 rule. Right? The maximum that you're allowed in planned comparisons will be K-1. You simply can't conduct any more than K-1. So if you have 10 groups, a few comparisons will be 9. Okay? Think about this not as objective view, but a relative. Because if you have 6 groups, the paired comparisons alone is 15. Okay? That's what we saw in the beginning. So conducting 5 out of 15 is already few. You're not conducting everything. Yes?
Can you do, like planned comparison, I know you could only have K-1, but for post-hoc test, can you do a planned comparison, like even if it's equal?
Again, if you have post-hoc tests,
Like if it qualifies for a planned comparison, can you also do a post-hoc test? I know you can
No.
do it the other way around.
you either do planned comparisons or post-hoc tests.
So post-hoc test can be possible if it's K-1 is maximum.
Post-hoc tests can be anything.
Oh,
We'll
so
see.
you can do it instead of
We'll see that soon. Okay. So here's an easy part. Okay. The calculation of a post-hoc comparison is exactly the same calculation as a planned comparison. Okay? The calculation of the comparison itself is no different. Meaning that the calculated f will not be different. For example, let's look at Seinfeld versus Louis C.K. So this is the formula for SS comparison. I can tell you now that there is no calculation in today's quiz. Okay? So you don't have to be stressed about this formula now. So today there's no calculation. You might be, like very simple algebra. But that's it. So what is this formula? What do we have here? Just a second. So we have the number of subjects and we have the weights, right? So we have weights. What's these weights? The weights simply represent the comparison. So if I'm comparing between Seinfeld and Louis C.K., I'll simply give Seinfeld a weight of 1 and Louis the weight of -1. Okay? That will put them both on different sides of the scale. So 1 and -1. And the last stop is the averages. So how will the comparison look like? 1 Seinfeld times 150, okay? 1 times 150, plus -1, right? The Louis C.K. weight, times 140. In effect, this becomes 150 minus 140 squared, right? In this point, only after you summarize weight times average plus weight times average plus weight times average, only then do you square it. Okay, so you get 10 squared in the denominator. Yes?
Do you have an example with more than 2? Because I feel like you would explain more.
Last lesson. If you want to see, you have to go back to last lesson. Today, I don't think we have another comparison. So, 10 squared divided by this, weight squared divided by the number of subjects. So I get that SSB, okay, look at this notation, SSB, 1 versus 5, okay? I think maybe Louis was 6. So 1 versus 6, okay? So simply the comparison, the SSB for that comparison. So if SSB is 500, MSB will be, who remembers? Who remembers from last lesson? MSB will still be 500, okay? Why? Because not only do we have two particular groups now, in planned comparisons, K will always be 2, right? Because we have two sides of a scale. Two sides of a scale, group 1 versus group 2.
That's only for the MSB, right?
Only
For the MSB?
for MSB,
Okay,
right?
it's 2.
So MSB is 500, and MSW, who remembers, is the same as the overall ANOVA, right? Okay, same MSW from the overall ANOVA. So we get 500 divided by 80, okay? 500 divided by 80, we get 6.25. That's our calculated F for this comparison. Now, if the calculation of F is the same for planned comparison and post-hoc test, where do you think do we find the difference? We have two sides. We have the calculated F and we have the critical F. Okay? After we calculate the F value, we have to find a corrected critical F. The only difference between the different post-hoc tests is the critical F. Okay? Each one will have a different correction to the F. What does it mean to have a correction? We're going to make the test stricter. We're going to make it harder for us to reject the null hypothesis. That's what that's making.
Do we have post-hoc tests that groups together as well that look like planned?
Yeah,
that are
yeah,
not
we'll get
planned?
it. We'll get it. Yeah.
So actually, there are more than 15 comparisons.
Right. Only for paired comparison. We'll get there soon. Yeah.
So we should correct the critical level with a more strict alpha. So you may not find anything, even though
Right.
the ANOVA.
Right. Okay. Alpha correction equals critical F correction. Yes. Yep. MSW will always be the same, and we explained it last week. Okay, so if you want to go back to it, go over last week. You also have the video, even though the quality is really bad.
And the MSB as well, no, isn't it supposed to be like significantly the same?
It would have been the same, not as the overall ANOVA, but the same as if we did this in plan comparison.
Oh, it's only a plan comparison.
Yeah.
We turn off the air conditioning.
Turn off the air conditioning?
No?
No, sorry.
No? Okay.
Sorry.
Just me.
Hey, bro.
Okay,
It's freezing.
new topic. Free class. Okay, new topic today. Alpha correction equals critical F correction. In order to control the family-wise alpha for alpha inflation, okay, we don't want alpha inflation. Shh, guys. Post-hoc tests reduce the alpha pair comparison. Now, you had this intuition last week. We have this formula. Okay, we have this formula. That's the formula for the family-wise alpha. Now, we have two ways to make sure that this altogether will be small. One is to make sure that we have a small amount of comparisons. Right? The other one is to use a smaller alpha. So, for example, if we conduct all the 15 paired comparisons, we get to 0.54. We saw that in the previous slides. But if we use, instead of 5% alpha, we use 1%, oh, the value comes down from 54 to 14. Okay, that's better, not great, but better. If we use 0.001, we get 2%. So the smaller the alpha we use pair comparison, obviously the smaller the family-wise alpha. Okay? So this is way too liberal. This is pretty liberal. And this is too strict for us already. Okay? 2% is, we went overboard. Now, is this idea clear? Right? It simply stems from this formula. Use a smaller alpha, have less alpha inflation. Now, whenever we use a smaller alpha, the critical F increases. What does that mean? So let's look at this degrees of freedom within is 50. Why 50, not 55? Because in the table we don't have all the values. If we have 55, we round down. Okay? We round down to make life a bit more difficult for us. This is degrees of freedom within. These are the alphas. So that's what I said. And why 50? Because again, it's from the MSW. So if we have an alpha of 5%, right, that's the blue arrow, we have a critical value of 4.03. If we use an alpha of 1%, we get a critical value of 7.70, just a second. And if we use an alpha of 0.01, we get 12.22. So the smaller the alpha, okay, the larger the critical value. Now it's a bit difficult to remember all of this, okay? What I want you to remember is that the smaller the alpha, the more difficult it is for us to reject the null hypothesis. which translates into a large critical F. But that's the main thing. The smaller the alpha, the more difficult it is for us. And if you remember, if I say it's difficult to reject the null hypothesis, it means I have less what? Power, right? The more difficult it is for me to reject the null hypothesis, the less power I have. Okay, questions on this one? Yeah.
So are we just guessing, or is there a systematic way to reduce it?
There is a systematic. We'll see that in a second.
Wait, how do we decide what alpha we use?
Good question. Next slide. So, larger F equals less chance of type 1 error, but also less statistical power. Okay? That's the main take-home message from post-hoc tests in general. Okay? Think about it. If we have less statistical power, in general, we prefer to conduct planned comparisons. That's it. Right? We always prefer the test with the more statistical power. Unless we can't help it. Yes?
Larger critical F?
Larger critical F. Right. Sorry. Larger critical F. I'll correct it in that slide. Larger critical F. Absolutely right. Okay. Good. So, how to choose the correct alpha? Right? Are we just guessing, or we have anything systematic that we're relying on? So, the exact alpha correction depends on the statistical test chosen by the researcher. Right? We have post-hoc tests in plural, right? We have many post-hoc tests, not just one. So each test will have a different alpha correction. Now, we're going to teach you only three. Three who are really the most popular ones. Okay? The general concept is the more comparisons we have, the harsher the correction. Right? Because we want to avoid alpha inflation, so the more comparisons that are taken into account, the harsher the correction. The first test is called Bonferroni test. Yes. So we're afraid from alpha inflation, right?
Right.
So we know that the more comparisons we conduct, the larger the family-wise alpha.
But not in post and not in post-hoc.
In post-hoc, we have different corrections. Now, you'll see how the different corrections work with this concept, right? Okay, each correction will be a bit different. But all of them due to this rule, that the more comparisons we're taking into account, the harsher the correction we should do. You'll see in a second. Okay. Maybe it's a bit vague.
By the word harsher.
Harsher meaning a larger critical F. So let's look at Bonferroni test. That's the really easiest one to understand. It's really straightforward. Now, again, test, Bonferroni test, but the calculation is the same, right? The calculation of F, of the calculated F, is the same. The only thing that changes is the critical F. So sometimes you'll see, just a second, sometimes you'll see it's called not Bonferroni test, but simply Bonferroni correction.
Wait, so this is the top alpha.
Yeah. So the Bonferroni test is really simple. Divide the regular alpha, 5%, by the number of comparisons the researcher is interested in. So The researcher is interested in a certain amount of comparisons. We concluded that the comparisons are not orthogonal. Okay? It doesn't mean that the researcher is now blind to the original hypotheses, right? Maybe he has or she has 3 comparisons which are not orthogonal. Okay? We want to give the researcher tools to conduct the best comparisons or the most powerful comparison he or she can. So the Bonferroni correction is simply take the alpha, divide by the number of comparisons, and get a new alpha. So we remember that this is the original comparison we're talking about right now. Okay? We're talking about one comparison, but remember Seinfeld was interested in 15 comparisons. Okay? He was interested in 15 comparisons. So 5% divided by 15, we get 0.003. There is no 003 here, so we round it down to 0.001. We rounded it down to 0.001, that's a sec. And we see that our calculated F is 6.25, and the critical F is huge, right? 12.22. So this difference cannot be considered significant when we use this kind of Bonferroni correction. Okay? We use the Bonferroni correction to correct for 15 comparisons, right? Seinfeld was interested in 15 comparisons, and he gets a really harsh correction to the alpha. Now, I just want to ask you, what would happen if Seinfeld was interested only in 2 comparisons? Right? Let's say you want to compare himself to Louis C.K. and himself to Chris Rock. Okay? Only 2 comparisons. 2 comparisons would mean that the alpha would be simply divided by 2. Then we use an alpha of 0.25. And now the comparison is considered significant. Right? So in one situation, it's not significant. In the other situation is significant. What's the difference? The correction becomes stricter and stricter and stricter the more comparisons we're interested in. Right? Because the more comparisons we conduct, the larger the alpha inflation. Yes?
Aren't you raising here the chances of the type 2 error?
Yes, absolutely. The less power we have, the more chance of type 2 error we have. Right? But we said that type 1 error is called type 1 for a reason. It's more severe, so we're more interested in avoiding type 1 error than we are in avoiding type 2 error. Yes?
But you said like the 5% is greater than 2, but it's not. 5.34 is bigger than 5%.
No. Look at the F, right? Calculated F versus critical F. Right? Yes, please.
Why are we, we're not really raising type 2 error because the overall family-wise alpha is going to be around 5%. So
Yes, but
in the
for
end,
each comparison, right? For each comparison,
what we're really interested in is, if he's interested in doing more comparisons, then he's interested in something. He could have done just done one comparison.
if he's interested in one comparison. If he's interested in one comparison, yes, you should have done just one
If
comparison.
he's interested in all of them, the overall alpha will be about 5% for everything.
Yeah, but the power for each one of the comparisons will be very, very low.
But it gives us like the numbers on the right. Is that the F, the critical F?
So we have the alpha,
Yeah, and then
that's the critical F.
so it's bad if the alpha is smaller because the critical
Again, it's
the critical F becomes bigger,
right.
so it's harder to reject.
Right, exactly.
So it's good.
It's bad for us as researchers. If it's harder to reject,
Yeah, but then if you reject it, that means that it's really
a strong effect,
Yeah.
right? But it's not good for us, right? Because you have this effect, which will
yeah, but
become
you make less mistakes.
you make less mistakes. That's true. But then if you make such a strict correction, you won't find anything. Yes. First of all, theoretically, why do we need a harsher correction the more comparisons we have? Because the more comparisons we have, the larger the alpha inflation, right? The larger the alpha inflation, the more we need to control for it. Okay? So this really exemplifies this idea. If Seinfeld is interested in 15, then he corrects so much that he can't reject anything. If he's interested in 2, that's fine. Yes?
You always round down.
Yeah, we always round down.
It's like 0.09.
Yeah, it seems a bit silly. It's only because we're calculating here by hand. In the program, you won't need SPSS. You won't need to round down. Yeah.
If, for example, you want to control for the amount of comparisons, would it not be just smarter to do a plain comparison? Because if we have 15 comparisons we want to do, we want to.
But again, if you have comparisons which are not orthogonal.
So if you want to do Jerry and Louis K and Jerry and someone else.
Right. Exactly. Sometimes we're not in the rubric of planned comparisons simply because the comparisons we're interested in are not orthogonal. That's fine. We're allowed to do that. Think about it this way. If your comparisons fit in neatly into planned comparisons, then do that. Otherwise, you have to do a post-hoc test. Okay. So, Bonferroni correction is considered a conservative test. It's considered a conservative test. It has reasonable statistical power when the researcher is interested in a small number of comparisons, but low statistical power when the researcher is interested in many comparisons. Now, it's weird to think about it. What's a conservative test? It means that not only it corrects the alpha, it ruthlessly corrects the alpha. Okay? If you remember from previous slides, when we use an alpha 0.001, we went overboard, right? Not only we have family-wise alpha of 5%, we have family-wise alpha of 2%. We use such a strict regulation that we went overboard. But that's the test, okay? And that's why we usually use Bonferroni only when we have few comparisons. Now, how few is a few? You'll never be asked that, okay? We're never going to ask you, is it few enough comparisons for us to use a Bonferroni test? That's not the point. We'll never ask you about that. You just have to know that the more comparisons the researcher is interested in, the harsher the Bonferroni correction. Yeah.
If we test the no by 1%, will the 0.0% there always be the same, or will it be 1%?
Again.
If we test the no by 1%,
yeah,
the Bonferroni will use the 1%, or it always uses the same calculation with the 5%?
So the calculation.
The number.
So if you
yes.
begin with an alpha
yes.
of 1%, so I don't know why you would want to begin with an alpha of 1%, but if you start with an alpha of 1%, yes, you divide your alpha by the number of comparisons. Yeah.
I don't know. I'm just having a hard time seeing why when you use many tests, because when I'm calculating here, I did it for 25, and it gives me an overall alpha of 5%. I understand for each comparison, it lowers our power.
Yeah, right.
But if we do a million tests, we're likely to find the result somewhere, even if our alpha is
somewhere. But you want all of them. You're interested in all of them.
But I don't think there's going to be a difference every single time necessarily.
We can discuss about this issue, I think, amongst us later. But the general idea is that you have less power. You can't really aggregate power the same way you can aggregate type 1L. Not really. Okay, so that's the first test. Pretty easy, I think, right? Simply take the alpha, divide by the number of comparisons, and you're finished. Second test. Actually, I want to hide parts of it. So let me delete some of them. Okay. So we said that Bonferroni is pretty conservative. So we have alternative methods. An alternative method is called Tukey honest significant difference test. Tukey test. Okay? Tukey test. Tukey corrects the alpha to compensate for all the possible paired comparisons. Notice, all the possible paired comparisons, not just the comparisons of interest. Okay? Not just the comparison of it. What does that mean? Let's say I'm a different researcher, okay, and I'm reviewing Seinfeld's study. And I want to conduct only, let's say, 5 paired comparisons. And I decide to use a Tukey test. Okay. Tukey will correct the alpha as though I did all the paired comparisons. Tukey doesn't ask me, how many comparisons are you interested in? He simply asks me, how many groups do you have? Of course, the more groups you have, the more possible paired comparisons you have. So, let's look at the way it is calculated. Is this idea clear of correcting for all the possible comparisons and not the comparisons of interest? I'll show you the formula. So this is the F, the critical F for Tukey. It's simply called FQ instead of FC. FQ is the critical F for Tukey. FQ equals Q squared divided by 2. What's this Q? Q is taken out of the Q table. Okay? You have a new table called Q table, which is comprised out of, again, columns and rows. The rows is degrees of freedom for the L term. Okay? The rows is as usual. The columns is not degrees of freedom between, but the number of treatments, the overall K. So, in this case, I, by mistake, went to 40 instead of 50. My mistake, it's supposed to be 50. Okay? So, degrees of freedom within. How many groups did we have in the overall ANOVA?
50.
We had
50.
6 groups, okay? 15 comparisons, but 6 groups. So, all the way here, okay? So, we have this number. It's not really this number because it's not 40. And we get that the critical Tukey, okay, is 8.94.
I don't understand how you got 4.23.
Again?
How did you get 4.23?
So again, we have this formula, okay? Look at this formula. So this is the formula to find the critical Tukey value. Is that clear? Idea?
Yeah.
Okay, you have the Tukey test. Shh, guys. You have a Tukey test. The Tukey has a different critical value than the other test.
Okay.
How do you find the critical value? By using this formula. The Q value is simply taken out of this table. Okay, if you see in the Moodle,
How do you get Q?
how do you get Q? So you have degrees of freedom, okay,
Okay.
and K, number of treatments.
Oh, and then, okay.
Okay, so you go down. It's not really 40, it's supposed to be 50. And then you're looking at how many treatments you have. Now, even though your degrees of freedom between is 1, the overall number of treatments is still 6. So 6, you get 4.23, you get this value. Yes?
Why don't they put Q squared? Why don't they just put it on the table? Like, do we use Q for anything else?
No, not for us. If you want, you can write yourself in an alternative Q squared divided by 2 table, if you want. Yeah.
What's the number for the columns? The upper?
K, the number of treatments,
And then for the rows?
the degrees of freedom.
So like the whole number of
For
participants
the
minus
rows,
one?
it's degrees of freedom.
That is like n minus 1.
N minus K.
And
And here is the number of treatments.
We have no idea how we got to that Q, right?
Okay, guys, listen up. I have to continue, otherwise you'll have less and less time for the quiz, okay? So, I want to make a point here. The calculation, you can go over it with the TAs, it's not the main thing. So, first of all, in this case, okay, then we see that the correction makes the test not to be significant, okay? That's what we have when we have 6 groups. But what if we had only 3 groups? Okay, let's say we had only Seinfeld, Chris Rock, and Louis C.K. In that case, K equals 3. Okay, K equals 3. And then the critical Q, the critical value for Tukey, is 5.92, and now the result is significant. So again, you see, the stricter the correction, the less likely a result to be significant. Now, the main point here is that the more groups we have, the more possible comparisons we have. The more possible comparisons, the stricter the alpha correction. Now, again, it's not about the comparisons of interest. It's just about the possible comparisons. So Tukey correction only cares for the possible comparisons and ignores the amount of comparisons the researcher is interested in. So if
possible comparisons, what you really do.
yeah, right? Because I'm going to calculate the comparisons I'm interested in, but the correction will take into account all the possible comparisons I'm allowed to do. Yes?
How do I calculate the family-wise alpha now?
Don't bother yourself with it. Okay? Just consider it that we corrected it. Okay? Roughly to 5%. Yes.
So if you get 5.92 and it's smaller than the critical F 6.29, then it is significant.
This is the F we calculated before.
Okay.
And it's larger than the critical F.
Okay.
So it's the same in this test and the one before?
Only it doesn't care about how many comparisons you're
But the
interested
whole
in.
group wants to be out.
Yeah. Okay.
Is the participants also?
Yeah, as usual.
More participants?
Yeah. Not stricter, it's easier. That's as usual. Okay. I have 2 more points to express and then we can continue. Okay? To the quiz. I'm sorry we don't have time. So Seinfeld conducted all the comparisons using the Tukey test. But he was also interested in the following question. Is he a better comedian than the rest of his friends on average? On average. So, look at the weights. 5 versus -1, -1, -1, -1. So this is not a paired comparison. This is a complex comparison. Right? Agree with me? This is a complex comparison. Now, Tukey test is only meant for paired comparisons. If you're conducting even a single complex comparison, you cannot use Tukey test. Okay? Again, if you're using at least one complex comparison, you cannot use a two-key test. Instead, what you have to use is called a Shafet test. Shafet. Never mind the name. Shafet. That's the name. You can also both.
What is complex comparison?
When you have not a paired comparison, right? Before we had Seinfeld versus Louis. Seinfeld versus Chris Rock.
That's a complex.
That's a paired comparison. A complex, we said it last week, when you have a combination of groups. I'm going to make a very short point. Okay? The short point is this. Shafet takes into account not only the paired comparisons, but also the complex comparisons. So now I have even more comparisons I'm taking into account. So this is one, but there are so many possible complex comparisons. This one, and this one, and this one, and this one, and on and on and on. We have a lot of complex comparisons in a set of 6 groups. So if Shafet takes into account all the possible comparisons, not the comparisons you're interested in, but all the possible comparisons, which do you think is more strict? Shafet or Tuki? Shafet, of course, right? And if you understand that, you understand the general gist of it. Okay? Many possible comparisons, strict alpha correction. I'm going to skip the formula of how to calculate the critical F for Shafet. You're going to go over it with your teammates.
But Turkey was actually less strict than the first one.
Right. So again, we have a lot of comparisons. Now the only thing you have to know is that Shafet is stricter than Tuki. Okay? Always and always and always. Here's an example. So these are the critical Fs for planned comparisons, for Tuki, and for Shafet for the same amount of people and the same amount of groups.